Yeah, hi everyone. So my name's Sam. So I'm at the University of Sydney, and today I'm talking about real-time decoding and some work that I've just finished with my supervisors Ben Brown and Stephen Bartlett. So before I begin, I just want to give a quick high-level overview of what I'm talking about. So I'm going to be talking a lot about decoders. I know we just heard a talk about decoders, but just quickly, for those of you who don't know, so when you do quantum error correction, you measure stabilizers of some code, and these measurements are giving you a clue about what error might have occurred. And so what a decoder is that it's a classical algorithm that just looks at the outcomes of stabilizer measurements and just tries to take a best guess at what error it thinks might have occurred so that you can correct that error and so on. And so in this work, the idea is to break up a decoding algorithm into pieces to try and get it to fit onto a real device, because it's quite a hard thing to do to actually take sort of standard decoding algorithms and without modifying them, put them on a device to run in real time. That's a challenging problem. Okay, so I think this is a cool problem to work on because it's very practical, but at the end of the day, we want to do a quantum computation. I also think it's quite an interesting problem because you take all this body of sort of decoding theory that exists, and then you kind of need to talk to people who have devices, and you need to start asking, okay, how can these algorithms be broken up? Where can processing be done on real devices? What are the bottlenecks? What are the constraints that exist? And so on. So it's kind of a multidisciplinary problem, but it's also quite important. Okay, so one of the key concepts that we use in this work is a concept that was introduced by Nicola actually back in 2020. It's this idea that you can break up a decoding problem into two stages. And why would you want to do that? Well, you want to do that so that one of those stages can be kind of put really close to the device, close to the quantum processor. It's a super simple stage, and that's cold. That happens in the fridge. And the other stage is going to be a room temperature, sophisticated decoder that's going to kind of complete the correction, if you like. So why would you do this? Well, you do this because there's certain bottlenecks that exist when you try and do real-time decoding. Things like having to make your decoder run fast, things like the bandwidth that you have to maintain when you pull data from the cold temperature to room temperature. And so you're trying to break up this problem so that when you do this first simple pre-decoding stage, you reduce the complexity of the problem that needs to get sent to and solved by the room temperature decoder. So we use this existing idea of a hierarchical decoder, and what we do is that we take the pre-decoding stage and we basically try to just ruthlessly optimize it to be as simple and as fast and as low bandwidth as it possibly can be for sparse errors, and then we see how it performs in the more adversarial case, in the case closer to threshold. Okay, so and so this is this cartoon picture that kind of reflects this idea that on the left we have to pull all the syndrome data out of the fridge and send it to some complicated room temperature decoder, and on the right we hope that we have some really simple local decoder that tries to do something at low temperatures, and then this reduces the complexity of the problem that you have to send out of the fridge. Okay, cool. So we did just have a talk about real-time decoding, so I'm going to try and keep this brief. I do want to take a step back though and tell you why you should care about this problem. Also, maybe from a slightly different perspective from Luca's talk, because I'm going to emphasize some of the bottlenecks that exist when you do try and do this. So this is a quantum error correction talk. So you need to know a little bit about a quantum code. So we're working with the surface code here. All you need to know is that when you see errors on the surface code, in your syndrome, that gives rise to pairs of defects. And the decoder only sees the pairs of defects. It does not see the error. And so the job of the decoder is to kind of to pair up these defects that it sees so that it can guess what error chain might have led to them. So that's all you really need to know about the surface code. But one of the key things is that when you start trying to do quantum error correction, you can't just measure your stabilizers once. You have to repeatedly measure them in case any one of those measurement outcomes was incorrect. You need to be robust against that. So what you're doing is you're sort of generating this stream of measurement outcomes. And this is the rate at which you're generating this stream of measurement outcomes is going to depend on the device that you're using and the architecture. But what's important is that it's this relentless stream of data that you're going to have to process. Even if you want your qubit to just be sitting there and not really doing anything, you still have to be doing error correction on it. You still have to be processing this kind of relentless stream of data. So when you go to process it, there's two bottlenecks that arise. The first is that this syndrome measurement data is generated at cold temperatures in the fridge. And you probably want to solve some of the decoding problem at least at room temperature on a conventional processor. So you're going to need to take all this data and lift it out of the fridge. And that's actually like quite a large bandwidth that you're going to have to maintain. And so this is one bottleneck that exists when you try to do this in real time. The other bottleneck is, of course, when you actually try and solve the decoding problem and return a correction, that doesn't take zero time either. That takes non-zero time. Right. So what's the time scale there? So, well, that's set by the clock speed on your classical computer, and it's set by the scaling of the classical decoding algorithms that you're using. So what's important is how do these time scales how are they related to the timescales at which this stream of measurement data is being generated? So in Luca's talk, I think this would be like the F that he was talking about. And the point is that if you're not keeping up with this relentless stream of measurement data, you're going to fall behind. So you need to be able to do this in time. And it's also important to emphasize, by the way, that if you're not keeping up with the rate at which this measurement data is being generated, it's not just like, oh, we're a bit slow, so our computation is going to be a bit slow. It's not like that. It's like you're failing to actually keep up with correcting errors that have the potential to completely ruin the computation. So it's like no computation if you can't keep up. So this is the idea of real-time decoding. Now, I just have a quick slide that I'm not going to spend too much time on because I know we have a few talks on this, so I think you'll probably get a bit of the different flavors of real-time decoding. All I'll say is that I think for context in relation to the last talk, the pre-decoding stuff I'm going to talk about is probably more like one of the inner decoders that you might run. So we're not talking about like so much scalability things here. We're talking about optimizing and trying to build a really fast, I think it would be like an inner decoder in the context of this inner and outer decoder stuff. Okay, so what are what is this super simple pre-decoding stage that we apply here? Okay, so they're really simple rules that we apply, and I can explain them to you here. So the idea in quantum error correction, like I said, and decoding is that you have pairs of defects, and you've got to try and match them up. And it's true, actually, that if two defects are closer together, then it's more likely that you should make that matching. You should prefer to make that matching. So an obvious first step to do with the pre-decoder is just to take any pairs of defects that are nearest neighbors and just match them up, get rid of them, take them out of the syndrome. And then pairs of defects that are further apart, that aren't nearest neighbors, what do you do with them? You just leave them there. It's fine. And you let them get passed off to your room temperature standard decoder. Okay. And so while you're doing this, remember, you're doing this so that you're reducing the number of defects that you see in the syndrome, so that the complexity of the problem that gets sent to and solved by the room temperature decoder is reduced. So let's walk through some of these steps. So maybe I'll just make one click and explain what's happened here. So on the top left, we have, so circles here are qubits, by the way. White circles are qubits without errors. Yellow circles are qubits with errors. And the yellow squares are defects. And so the decoder sees the squares, but it does not see which qubits are yellow and which are white. So in the top left, we have a pair of nearest neighbor defects. And the pre-decoder has seen that they're nearest neighbor defects, and it's just paired them up and removed them from the syndrome. In the bottom left, we have a pair of defects that are not nearest neighbors. It's a small little chain here. And the pre-decoder has gone, let's not touch that. Let's not do anything. OK, fine. In the top right, we have a more complicated error configuration. Just to explain what's happened here, well, we really had 3 pairs of nearest neighbor defects in the top right. So the pre-decoder has executed its algorithm simultaneously here. So it's seen 3 pairs of nearest neighbor defects, and it's placed a correction between all 3 of those pairs. In this case, that middle qubit there did not initially have an error on it. So in this case, it's kind of done something wrong, which we'll see it does do something wrong every so often. And it's left over an error there at the end of the day. OK, so that's cool. So that's how it works on quite a contrived sort of error configuration. We might think about using this thing at error rates of something like 1% or less. So this is an error configuration at 1%. And this was generated. And then, of course, what happens, I mean, you can predict what happens when you run the thing and just sees them all and OK, so it cleans them all up. So it's a bit silly, but the point there is like that is what most errors look like at 1%. That is a 1% error, and so the point is that most errors at 1% are you don't need to throw some sophisticated decoding algorithm at them. Most errors at 1% just can be cleaned up in a super simple way. And what's important about that is like we actually care about speed and bandwidth and all these things on all of these errors, even if they're easy errors. So we should just be throwing an easy decoder at these things. OK, cool. Yeah. OK, so what do we expect to come out of running this thing? OK, well, what we've done here is that, remember, so we've removed all pairs of nearest neighbor defects from the syndrome. So what we now need to generate a pair of non-nearest neighbor defects is we need 2 errors to occur nearby each other in the code so that you can create a pair of defects and then you can kind of like separate them by some distance. Only then will the pre-decoder fail to clean that up. So we call this like an order p squared event as opposed to an order p event because it occurs with probability p squared. So we're expecting a reduction in the defect density by a factor of p. And by the way, when I say defect density, this is a proxy for the bandwidth required and the runtime of the standard decoder, because this is really the size of the problem that you're sending out of the fridge. OK, so just quickly here, I mean, how are we modeling this thing? So in general, we expect this defect count to be Poisson distributed. So in some space-time volume V, we expect that if m is a random variable corresponding to the number of defects, it's Poisson distributed. And rho here is really the parameter that's telling you the defect density that you expect to see. And so what's important is that we're expecting rho to go from scaling like p with some prefactors to scaling like p squared. And so this is also a reduction to the bandwidth and to the runtime usage. OK, so yeah, indeed we see this. So this is a plot of the mean defect density in the code with pre-decoding in blue and without pre-decoding in green. So yep, this is cool. So for error rates of 10 to the minus 3, you see several orders of magnitude improvement here. Yeah, that's great. And these slopes, by the way, yeah, they correspond to the p and p squared scaling that we're expecting to see. What else is quite nice, by the way, is so we actually plot the full histogram. So here, this is data, and I've just plotted a histogram of the number of defect counts that you see in these syndromes. And so, yeah, so the solid lines here are the theory lines, and then the shaded regions are the numerics. And what's quite nice about this is that, this bandwidth and runtime reduction is really coming from just a reduction in the density of defects that you see. So the reason this is nice is because the total defect count kind of gets averaged over the whole space-time volume of the decoding problem, which means that these quantities are only going to fluctuate a little bit, like not too much. And so it seems likely, I'm not an experimentalist, but I'm told it seems likely that when you try and do real-time decoding, you really want every stage of that process to be, timing-wise, you want it to be as deterministic as possible. And so the fact that these quantities might fluctuate a little bit, but not too much is quite nice. The other reason this is nice is that because it's a reduction to the defect density, we expect that, this should equally apply to really large space-time volumes. So it's true that this work on parallelization makes me think maybe this is not as relevant as I previously thought. But still, you can straightforwardly apply this to as large space-time volumes as you want. You really don't need to worry about that. Yeah. Okay. Cool. So the big question is, what's the cost of running this scheme? So we did something super simple that was just optimized for sparse errors only, and so we expect to take some hit in terms of the cost of the scheme. So I'll be really brief here. I'll just highlight like the main factors. So one of the things that really kills you here are these errors like this. So this error is constructed by taking an error on 2 consecutive qubits and then leaving a gap, and then taking an error on 2 consecutive qubits and then leaving a gap. And remember, the pre-decoder or any decoder doesn't see the error, it just sees the defects. And so what it sees here is a pair of nearest neighbor defects, and then a little gap, and then a pair of nearest neighbor defects, and then a little gap, and so on. And so what it's going to do, it's going to come in and pair up those nearest neighbors, and in doing so, it's going to increase the weight of this error string. So that's something bad. Like that's a problem. And so in this work, we don't try and correct these sorts of errors, but we do study them in quite a bit of detail and try to work out just how much they cause problems. And it turns out that they're not as bad as they initially seem, and there's 2 reasons for that. So the first reason is that there's just not that many of these errors. In fact, it's quite you have to be quite precise about how you construct these things by taking the 2 errors and then leaving the gap, and then the 2 errors and so on. So the combinatoric factors here are actually quite good. So there's not many of these errors. The other thing is a finite size effect. So if you think about an error chain like this, the smallest error chain you can have like this is if you have error, error, gap, error, error, and then so that's a weight 4 error that's going to get filled into a weight 5 error that could potentially cause a failure on a distance 10 code. So errors like this start to become important up beyond distances of 10, but there is a finite size effect here that means that these things actually aren't so bad for smaller distance codes anyway. So we do quantify the cost of this scheme. The way that we do that in quantum error correction, of course, if you're below threshold, then bigger codes are better because they give you smaller logical failure rates. Bigger codes are also more expensive because you need more qubits to build them. So the way that we quantify the cost of this scheme is we say, okay, we're going to fix a target logical failure rate, and we're going to ask, how much bigger do I need to make my code so that we reach those fixed target logical failure rates when we're including the pre-decoding? So this is like a qubit cost associated with the fact that we want to run the pre-decoder to get these reductions in bandwidth and runtime and so on. And what we see here is that we see quite a modest, I think, a 50% increase in the number of qubits over a wide range of physically relevant error rates. So by the way, I know there's a lot going on in this plot here, but that would be the right-hand axis on the inset is the factor increase in data qubits required to accommodate the running of the pre-decoder. So that is a 50% increase across a wide range of error rates. Okay, so just to summarize, what have we done? We've started with existing ideas about hierarchical decoders and how they can be used to make these bandwidth savings and these runtime savings. And we've taken the pre-decoder and we've tried to optimize it as much as we possibly can to be as simple, as fast, and as low bandwidth as we can make it. By the way, we've made it as simple as we possibly can to give it the best shot at being something that might be able to be implemented at cryogenic temperatures. You want something super simple. I mean, this is just a few gates of classical logic. And this has come at a modest cost to the qubit count for the scheme. What else might we think about? Well, we might think about trying to recover some of the logical failure rate that we lost. We've got several ideas for thinking about what to do there. I won't go into them right now. I don't know where I am on time, but yeah. 7 minutes. I will go into a few of them. Okay. Let's see.
If you didn't, I would ask you anyway.
I thought you might. Okay, so one thing that we try to do, I'll talk about two of these ideas because one of them we did and one of them I think is pretty cool. So the one that we did is that we introduced a parameter to this family of pre-decoders. And what we said is, okay, we don't want our pre-decoders to be quite so greedy. So if we see a pair of nearest neighbor defects, we just want to make sure that they're reasonably well isolated from any other defects in the code before we commit to making that correction. So R here is some parameter that's capturing, if R is big, it means we're being more cautious about our pre-decoding stage. And so what you can see is that we still see order of magnitude savings in the defect density and so on, but they only kick in at slightly smaller error rates, and you lose some of those savings, which of course makes sense. You're making fewer greedy corrections. But in terms of the cost of running this thing, it comes right down. So in particular for R equals 2, we find this cost is nearly negligible, and I believe that makes sense because of some of these finite size effects that we talked about. So for R equals 2, if I go back to these error chains, you actually need like, I'm not going to get the number right, but it's like error, 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 gap. Error, 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 gap, and so on. And so there's these finite size effects that mean that actually for small codes, this thing doesn't really cost too much at all. So that's one thing that we did. The other thing I think is cool to think about is this third one, which is comparing multiple corrections. So you can use sort of standard decoders to, okay, so the standard decoder that we use is called minimum weight perfect matching, and it gives you the most likely correction for a particular configuration. But in fact, you can use it to compute the most likely configuration in each logical sector. And if you do that, then you can kind of compare how likely the correction was between each logical sector, and you can work out how confident you are in the correction that you've come across. And so if you do this, then at some point you can say, okay, I've run my pre-decoder, I've had all these bandwidth savings, great, this is really cheap. I've pulled this data out of the fridge. I've done some comparative thing where I've looked at the different logical sectors, but hang on, I've seen that I've got two corrections here and I'm not really sure which is the right one. I only marginally prefer one of them. And in that case, what you could do is say, okay, well, let's stop. Let's be a bit more careful. Let's go and ask for some of that data back. Let's pull out some more of that data that we kind of threw away in the pre-decoding stage. So I think that's a really cool idea because I think you could sort of, I mean, I think it would be an idea to try and sort of have your cake and eat it too, right? Because you can make all these savings most of the time, and then instead of having the pre-decoder stuff up, you just have the pre-decoder, you're able to just say, okay, I know that the pre-decoder was kind of getting a bit too greedy here, so I'll step in and be a bit more careful. So you can recover some of that hit to the logical failure rate. Okay, I think I'll stop there, right?
Thank you. We have time for a few questions. Yeah, towards the left and then towards the front.
Thank you for the excellent talk. A couple of small questions. So one, could you comment on, so what information is passed up by the pre-decoder? Is you pass on sort of do you have to pass on the syndromes that you detected, but also things that you think you should correct as well?
So let me go back here. So it's a good question. So by the way, what I haven't said explicitly is you're really passing out like the addresses of the defects in the code. So the message is going to that you're passing out is going to scale in the number of defects that are left over. So what you're doing here, right now, if I didn't do pre-decoding, right, I would be passing out 1, 2, 3, 4, 5, 6, 7, 8 addresses, because there's 8 defects there, so I'd be passing all of them out. I do the pre-decoding and I clean up some of them, and here I pass out 3, 4 defect addresses. So does that answer your question?
So the ones that you sort of corrected away, does anything above the stack need to know that you've resolved that? So do you need to communicate that, or is that? So
no is the answer. That does not come out of the fridge. That's part of the problem, is because in a sense you have these regions like the room temperature decoder does not know whether the pre-decoder has applied a correction or not, and that's what kind of leads to this loss in logical failure rate, because it is a greedy thing to do to just like throw away some information. But what that does mean is it can be implemented like pretty just aggressively, like super simply. If that would be a drawback to one of these things, like I was thinking about with the comparative stuff, is that, well, if you wanted to do that, presumably you are going to have to store all that pre-decoded data somewhere if eventually you're going to want to recover it and do something with it. So yeah, if you wanted to implement that scheme, it would probably be a bit more complicated. Yeah.
Thank you.
Right here next.
Yeah, hi. Thanks for the good talk. So I found your scheme, and yeah, yeah. So I found the setup fairly reminiscent of David Perlon's RG decoder, where you sort of like estimate local error probabilities for local regions and then pass it on to higher layers. Have you thought about combining this kind of setup with like local soft decision decoders or error probability estimation routines in order to improve the decoding step, or do you think that's too costly? From
it's a good question. I think it is reminiscent of that. You can sort of think of this as just like one step of an HDRG sort of decoder. What we really wanted to do is like basically just try and see what comes out when you do like the simplest possible like thing that you can do. So yeah, like I say here, I mean, you know, I think it's very challenging to implement things in fridges, right? There's a whole bunch of constraints and I don't know too much about them, but I know that it is. So we're kind of trying to explore just like, okay, what happens when you do the simplest possible thing? I think that's a good idea, though. I think you could do something more complicated for sure with some soft information, renormalization group stuff, and you could cut it off at different levels. Here we just do HDRG, and we cut it off at the very first level, and then we say, okay, well, what falls out of that? What are the savings? What are the costs, and so on? Yeah.
Hi, thanks for the talk. What kind of error models did you consider? Was it just like deep learning noise on data qubits?
Yeah, sorry. So I didn't actually say that. All the diagrams I gave were in 2D just for I just find it easier to work in 2D diagrams, but it was phenomenological phase flip was the error model. Yeah.
Luke has a question. Go for it.
Sorry to come on from the side. Yeah. So how do you also resolve measurement errors, or how do you see this process of getting multiple rounds of data? You then accumulate the data before you send it to before you clean it up and send it to the global decoder, or do you like just resolve one round at a time these simple defects and then send that data up? Because if you need to like accumulate a lot of data, then you add latency.
Yeah, it's a good question. So we don't think of accumulating a lot of data. We think about just something that sort of sits on, I guess, like every qubit, and it just needs like a single bit to kind of store the parity of the pre-decoded correction on that qubit. And so you're not like collecting a whole load of data. At each round of syndrome measurement, it just needs to see what the measurements outcomes are one time step before and one time step after, and then spatially around it. And then it can update the parity of like the correction on its little qubit. So no, you don't need like some memory that's kind of, you don't need any memory in the fridge that's like keeping track of the whole, D rounds of measurement or anything like that, yeah.
Okay, so I know there's one more question. Make it quick, please, so we can get to the last talk.
Have you thought about how this process might work on other error correcting codes other than the surface code?
Yeah, I think it would be pretty straightforward. I think the same is true of hook errors as well. One way to think about it is like, anything that arises from just a single fault, even like circuit level noise, I think anything that arises from just a single fault is sort of like an order P error, so to speak. And so this thing is kind of just a lookup table almost that just says, do I see an order P error at a particular point? If I do, let's just get rid of it. And so, yeah.
All right, thank you so much, Sam.
Great, thanks.